Silence had settled across the solar system in a way that felt deceptively ordinary. Planets continued along their ancient circuits, drifting through the void with the predictable cadence that had defined 4.5 billion years of cosmic motion. The great gas giants rotated with their thunderous calm, the asteroid belts shimmered in muted chaos, and the heliosphere pulsed with its steady breath of solar wind. Nothing in this grand arrangement hinted that anything unusual was preparing to unfold. Yet the stillness of the starlit vacuum was not the stillness of peace. It was the moment before awareness, the pause before a revelation, the space in which reality prepares to rewrite itself. Somewhere far beyond the traditional boundaries of planetary vigilance, an object moved with a quiet defiance that no one had noticed yet. The first signals came as faint positional irregularities. Observatories monitoring routine interstellar debris catalogues recorded a handful of data points that at first seemed unremarkable. They were little more than dim flashes against the background stars appearing in wide-field surveys designed to track long-period comets and slow intruders from the outer Oort reservoir. These flashes did not invite suspicion. They did not carry warnings. They simply existed, logged and forgotten, like countless other entries drifting toward the sun from the far darkness. But the silence surrounding them contained the seed of a paradox. The object later named 3IATLAS was already bending reality in ways no one yet recognized. At that early stage, even fate seemed unaware of the consequences. Photons bounced off a small, cold surface and traveled for millions of kilometers to reach Earth. They arrived quietly at the sensors of robotic survey telescopes, forming fragile sequences of brightness values on distant screens. To the machines, it was only another point. To the human eye, had anyone looked at that instant, the object would have seemed like nothing more than a faint ripple in the tapestry of stars. Yet within that flicker lay the first expression of emotion that did not belong to the solar system. It carried with it memories of interstellar distances, the scars of environments older than the sun, and a trajectory shaped by forces that had acted long before human beings understood what orbits even were. The calm that enveloped the solar system became part of the story because it framed the contrast between what was stable and what was about to become unstable. Space had a rhythm ancient and unchanging, and that rhythm had been humanity's anchor. Astronomers built mathematical structures upon it. Space agencies shaped missions around it. Every spacecraft launched from Earth relied on the precision of gravitational geometry. Planetary science assumed the reliability of celestial mechanics. Against that backdrop of certainty, the slightest deviation becomes a monumental disturbance. In the early hours of observation, however, nothing in the data announced such a deviation. The silence held. The cosmic structure remained serene, but serenity in astronomy is often an illusion, a veil concealing dynamics that require time to reveal their meaning. The object's quiet approach gliding through interplanetary space masked a choreography that did not fit the gravitational patterns scientists expected. Even before the anomaly was recognized, the seeds of confusion were already present in the numbers. The motion of the object across the star field was a little too smooth, a little too consistent, and a little too detached from the faint cometary drift familiar to watchers of the outer sky. It behaved as if the solar system were merely a temporary corridor, not a gravitational well demanding obedience. That was the first unspoken disturbance. Something was arriving that did not care about local rules. As the hours and days passed, the silence surrounding its presence persisted. Observatories logged new data. Automated systems compared these points with ephemerides. Nothing yet triggered alerts. This was still the stage when the mystery lived beneath consciousness. It lingered in margins and uninspected tables, waiting for the moment when an astronomer would notice a shift too strange to ignore. But the object itself was already carrying the tension of a story that would eventually ripple through the scientific world. It was not approaching like a typical comet. Its path cut through space with an indifference that belonged to distant stars and interstellar winds, rather than to the sun's gravitational command. In those early recordings, the object's light seemed steady. There were no sudden outbursts, no classic signs of an active nucleus beginning to shed volatile ice. The darkness around it appeared undisturbed. It was the kind of silent visitor that would be catalogued and forgotten if not for the subtle defiance encoded in the motion vectors. These tiny angular shifts were the first hints that 3I/Atlas was not merely an exotic wanderer, but a messenger from regions where gravity behaves differently and time leaves different marks on matter. The solar system's edge had long been considered a boundary of calm isolation. Interstellar travellers occasionally crossed it, but their presence felt like distant events rather than immediate perturbations. Yet this object moved differently enough that the idea of isolation began to fracture even before scientists consciously acknowledged the break. The quiet environment through which it glided became the stage for a transformation in how humanity perceived the outer regions of the Sun's domain. The calm sky, unchanging for billions of years, was on the verge of revealing that it could no longer guarantee predictability. As light continued reflecting off the object's surface, carrying new clues toward Earth, the stillness of the solar system took on a fragile quality. It was the silence of a deep inhale before a startling revelation. The narrative of celestial mechanics was preparing to encounter a contradiction. For now, though, the object remained an unnamed point of faint brightness drifting soundlessly through the void. The planets continued their ancient circuits. The sun continued its unbroken burn. And no one yet understood that the stillness was not the background state of the cosmos, but the boundary of knowledge waiting to be crossed by the anomaly on its way inward. The first glimmer of 3IATLAS entered the scientific world without ceremony, a faint trace of reflected sunlight, recorded by the Atlas survey system on Hawaii's Mauna Loa. At the time, the detection resembled thousands of others, a dim magnitude point drifting slowly across the night sky, unremarkable within the relentless flow of data that automated telescopes accumulate each night. These systems are designed to guard Earth from potential impacts, searching for hazardous asteroids and long-period comets that slip inward from the solar system's distant reservoirs. Nothing in the initial images hinted that this new point of light was anything more than another icy wanderer, beginning its long descent toward the inner planets. But history often hides inside the smallest details, and this faint glimmer marked the beginning of a story that would challenge the foundations of celestial mechanics. The team overseeing the nightly scan noted the detection with professional caution. They assigned a provisional designation, plotted its early coordinates, and fed the measurements into the standard orbit determination software. The algorithms expected a familiar pattern, a path shaped by the sun's gravity slightly perturbed by past encounters with distant stars or molecular clouds. Early data offered only a whisper of motion too limited to define a clear trajectory, yet even this whisper carried a subtle discord. The displacement from one frame to the next was too linear, too clean, almost as if the object had not yet begun responding to the sun's influence. Such impressions were far too vague to draw conclusions from, yet they created a quiet sense of curiosity among the astronomers reviewing the observations. As additional images were captured on subsequent nights, the glimmer persisted. The brightness remained stable, showing no dramatic outgassing or coma formation, typical of a comet warming for the first time in centuries. This calm optical behavior made the object appear inert, like a dormant fragment of rock, rather than a volatile-rich traveller from the deep cold. But its refined positional data told a different story. The new coordinates did not fit neatly into the gravitational curve expected from any familiar orbit. Tiny deviations from predicted paths appeared small enough to be dismissed as measurement noise, but consistent enough to provoke interest among those who scrutinized orbital anomalies for a living. Within the astronomical community, the discovery phase of any interstellar visitor carries an atmosphere of alert fascination. The arrival of 1I/Oumuamua years earlier had set a precedent. Bodies that drift in from the space between stars often behave in ways that strain human understanding. With that memory still lingering in the background, some astronomers wondered whether this newcomer could represent another rare emissary from the galaxy beyond. Yet even that possibility did not fully explain the eerie subtlety with which this object moved. Interstellar bodies typically display high incoming velocities and sharp approach angles. This one arrived with an oddly tempered motion, suggesting a long, quiet glide rather than the dramatic plunge characteristic of objects falling from interstellar space. The glimmer recorded by Atlas soon formed a pattern of data points that drew the attention of additional observatories. Researchers requested follow-up imaging from pan-stars on Haleakala and from mid-sized facilities in Chile's Atacama Desert. Each telescope contributed new fragments of information, adding clarity to the object's position, relative velocity, and apparent spin characteristics. Yet clarity did not bring comfort. The object's path displayed an almost unsettling smoothness. It lacked the gravitational wobble expected from early interactions with the Sun's sphere of influence. Instead of curving naturally inward, it drifted as though it had been travelling on this line for eons and saw no reason to alter its course. This subtle defiance caught the attention of orbital dynamicist specialists who construct mathematical models for the movement of celestial bodies. They noticed that a purely gravitational solution produced residuals inconsistent with normal observational uncertainty. In simpler terms, the numbers did not line up cleanly. Something was wrong with the underlying assumptions. But at this early stage, the discrepancy was still hidden beneath the noise. A few more nights of observation were required before the anomaly would rise fully above the threshold of doubt. Even so, the sense of approaching revelation grew. Astronomers are attuned to patterns that break expectations. It is part of the discipline's culture to watch for the data point that does not fit the brightness variation that seems impossible, the orbit that refuses to behave. These are the clues that lead to new discoveries, and the first glimmer of 3I/Atlas held that same atmospheric weight. The researchers who examined the raw photometry noted that the object lacked the flickering irregularity typical of rotating comets. Its light curve showed a steadiness that belonged more to a compact non-fragmented body, suggesting that the object might be unusually cohesive or composed of material unlike typical cometary substrates. The glimmer also told a story about origin. Interstellar objects carry with them the physical memory of the environments they once inhabited. Their surfaces bear chemical signatures shaped by radiation fields, high-energy particles, and temperature extremes that differ from those inside the solar system. Early spectroscopic glimpses of the object hinted at a coloration that did not align perfectly with traditional cometary taxonomies. It was neither the dark carbonized tone of a long-frozen nucleus nor the reddish hue typical of trans-Neptunian objects. Instead, it displayed a muted metallic reflectivity that raised questions about its past. As discovery continued, the object earned its interstellar classification, becoming the third confirmed visitor from beyond the Sun's formative domain. This designation intensified the scrutiny directed at its motion. Astronomers around the world aimed their instruments toward the dim glimmer now moving through interplanetary space. Every new data point added depth to the mystery. The coordinates refined the trajectory, but the trajectory refused to conform. A disquieting subtlety lingered in the computations. It was not yet a full contradiction, not yet a dramatic violation of physics, but the early signs suggested that something unconventional was guiding the object's path. The discovery phase is often remembered later as the moment when the world first encountered an extraordinary phenomenon. Yet at the time it rarely feels extraordinary. It feels methodical, filled with calibration checks, statistical fits, and quiet discussions among scientists who measure reality with the precision of mathematics. The glimmer of 3I/Atlas passed through this process like any other new object. It simply offered answers that did not settle comfortably within known frameworks. This was the beginning of the story, a faint streak of light drifting across sensors, a series of coordinates that resisted familiar curves, a quiet visitor whose presence carried the prelude to a deeper disturbance. The solar system had noticed the arrival, without yet understanding it, and in the subtle defiance embedded in those first glimmers, the anomaly had already revealed the first hint of a motion that no comet should possess. The night the orbit twisted was not marked by any celestial spectacle visible to the casual observer. There were no sudden flares of light, no dramatic fragmentation events, no unmistakable signs that something unprecedented had just unfolded in the vast quiet above. Instead, the pivotal moment entered the scientific record through a series of ordinary numbers quietly plotted onto a graph by astronomers who expected nothing unusual. Yet within those numbers, hidden inside the precise coordinates of a faint interstellar traveller, the solar system encountered a deviation that would come to redefine the entire narrative of 3I/Atlas. In most cases, the refinement of an orbit proceeds with predictable calm. Early measurements contain uncertainty which gradually decreases as additional data constrains the object's motion. The path tightens, assumptions stabilize, and the resulting curve soon aligns with established gravitational expectations. The solar system is a realm of precision. Its language is mathematical, and its rhythms are ancient. But when the new nightly observations of 3I/Atlas were fed into the computation model, something subtle but unmistakable shifted. The updated trajectory refused to settle into the curve predicted the previous day. It resisted the correction. It reshaped itself. The anomaly did not announce itself as chaos. Instead, it appeared as a slight but persistent divergence. observers reviewing the ephemeris data noticed that the projected location differed from the actual measurement by more than the statistical noise allowed. At first they suspected an instrumentation calibration issue, a misaligned CCD pixel, a minor temperature drift, a rounding error. In astronomy, these small technical irregularities are common enough that they rarely trigger alarm. But when the next set of images arrived taken from an observatory thousands of kilometers away, the divergence persisted. The orbit was not drifting because of measurement error. It was drifting because the object itself had changed its motion. Orbit modelers approached the task with caution. They recalculated everything, rebuilding the trajectory from scratch using each available dataset. The new model produced an unexpected shape. Instead of curving gradually inward toward the Sun, the object traced a path that bent in a way wholly inconsistent with the forces acting upon it. There was no swing from Jupiter's gravity to explain the shift, no interaction with the faint pressure of the solar wind, no asymmetric outgassing jets pushing it sideways as comets often display when ices vaporize. The deviation was clean, smooth, and entirely outside the normal grammar of celestial dynamics. For an interstellar object, unexpected motion is not unheard of. Oumuamwa's trajectory had also shown non-gravitational behavior, a fact that ignited debates ranging from exotic physics to unorthodox interpretations of cometary behavior. But the twist observed in 3I/Atlas differed in tone. Oumuamwa had accelerated slightly along its outbound trajectory, a behavior that could at least be tentatively attributed to sublimation. In contrast, the shift in 3I/Atlas occurred inward during a stage when the object exhibited no signs of thermal activity at all. Its coma remained absent. Its brightness remained stable. There was no detectable tail of gas or dust. Yet the orbit bent as if a small but persistent force had nudged it. When the anomaly became impossible to dismiss, the astronomers submitted a formal notice to the Minor Planet Center, highlighting the deviation. Discussions began circulating across research groups. Emails moved rapidly between institutions in Europe, North America, and East Asia. The consensus was clear. The orbit had twisted, and it had done so without any mechanism recognized in standard cometary physics. Few scientists were willing to speculate publicly, but in private conversations the implications were already beginning to take shape. If this object was not responding to gravity in a typical way, then either something was influencing it externally, or its internal structure possessed properties different from anything previously encountered. The twisting of the orbit was more than a mathematical curiosity. It was a moment of intellectual fracture. Comets do not choose their paths. They follow gravitational fields shaped by the mass distribution of the solar system. Deviations occur only when physical asymmetry provides a counterforce, but here no such asymmetry was visible. The surface remained inert. The thermal profile remained cold. No outgassing jets appeared even in deep infrared imaging. The orbit had twisted without an explanation rooted in observable matter. As more observatories confirmed the shift, researchers began refining the anomaly with greater precision. They noticed that the deviation was not random. It followed a subtle pattern, one that seemed almost directional. The object was drifting slightly off the expected curve, but always in a way that preserved the smoothness of its motion. It was as though the object moved within an invisible current, gliding along a path that did not belong to the Sun's gravitational landscape. These early realizations triggered a wave of debate among dynamicists. Some argued that the dart could still hide an unseen gas jet. Others insisted that the magnitude of the motion contradicted such a simple explanation. Data from spectroscopic surveys deepened the confusion. If the object was shedding volatile compounds, the spectra should have revealed faint molecular lines from water vapor, carbon dioxide, or other common cometary gases. But the signals were flat. There was no chemical signature consistent with sublimation. The orbit had twisted cleanly without the physical processes that typically accompany any non-gravitational push. The contradiction illuminated a growing tension. The solar system had encountered a visitor whose behavior violated the intuitive links between cause and effect. The night of the twist soon became a reference point among astronomers studying the object. It represented the instant when the story transformed from routine tracking to profound investigation. In retrospect, it resembled the moment when a curtain rises revealing a larger stage than expected. What was once assumed to be a simple interstellar fragment began to resemble something far more complex. The twist signaled the beginning of a narrative that would lead to deeper questions about the origins of interstellar bodies, the physics governing their motion, and the possibility that some of them carry the imprint of environments radically different from the solar system. Within days, the anomaly crossed the threshold from quiet observation to global scientific attention. The orbit had twisted, the gravitational model had fractured, and the object named 3I/Atlas had announced not through light or sound, but through motion alone, that something extraordinary was unfolding in the space between planets. Tracing the origin of 3I/Atlas required astronomers to look far beyond the confines of the solar system, into stretches of interstellar space, where stellar winds intermingle and gravitational influences grow faint. When an object arrives from such immensity, its path carries the imprint of countless invisible encounters. Every close passage by a dying star, every brush through a turbulent molecular cloud, every drift through regions shaped by ancient supernova shock fronts, leaves subtle marks upon its velocity. To reconstruct that journey, researchers turned to the earliest available measurements and began extending the trajectory backward step by step into the unlit distances from which the visitor emerged. This process is far from straightforward. An interstellar object moves with a freedom unavailable to the icy fragments born within the sun's control. Its approach vector is not shaped by planets or the delicate gravitational interplay of the outer Oort region. Instead, it reflects the accumulated momentum of distant epochs. Even the tiniest discrepancy in early measurements can dramatically alter models when projected millions of years into the past. Yet despite this difficulty, a pattern began to form. The backward integration of the orbit showed that 3I/Atlas had entered the heliosphere at a glancing angle that did not correspond to any stable reservoir of local debris. The direction pointed outward toward a region of the galaxy not commonly associated with high traffic of interstellar fragments. As the orbital reconstruction extended further, researchers found themselves confronted with a curious implication. The object appeared to have drifted through interstellar space with an unusually calm velocity profile. Many interstellar bodies exhibit the signature of violent ejection forced from their parent systems by the gravitational chaos of forming planets or the upheaval of unstable binary stars. They tend to arrive with sharp high-speed vectors. But the path of 3I/Atlas suggested a more serene expulsion, or perhaps no violent expulsion at all. Its incoming velocity was modest by interstellar standards, almost contemplative, as if the fragment had been drifting for tens of millions of years without significant disruption. To understand this, astronomers analyzed the approach direction against the known motions of nearby stellar associations. They examined clusters within several hundred light-years, comparing their galactic coordinates with the incoming orientation of the object. One region yielded a faint correspondence, a loose collection of stars older than the Sun and scattered across a quiet corner of the local spiral arm matched the approximate backward projection. These stars belonged to no major hierarchical group, nor were they associated with dense nebulous formations that frequently generate free-drifting debris. If 3I/Atlas had emerged from such a tranquil region, that peaceful environment might explain its gentle entry into the solar system. Yet the quiet nature of that region introduced new questions. A calm, stellar neighborhood does not typically produce fragments large enough to travel interstellar distances unless some unusual mechanism intervenes. The object's origin demanded an explanation that did not rely on chaos but on slow processes acting over astronomical timescales. Researchers speculated about long-period orbital decay around a faint star. They considered the possibility that an ancient planetary system had gradually eroded, shedding material softly into interstellar space rather than violently ejecting it. Others examined whether the object could have been shaped by radiation pressure rather than gravitational upheaval. Through all this work, one detail maintained its importance: the path the object travelled before entering the solar system was surprisingly unperturbed. The backward model displayed no rapid directional changes, no erratic accelerations, no signs that it had tumbled through the gravitational turbulence of massive stellar bodies. Instead, the trajectory resembled that of a solitary wanderer, drifting through interstellar silence, guided only by the faint pull of distant stars and the steady drag of time. This serenity in its origin clashed with the confusion it created within the solar system. An object shaped by such quietness should have behaved predictably once influenced by the sun's gravity. The fact that it did not behave predictably sharpened the contrast between its distant past and its present anomaly. The backward tracing reinforced the idea that whatever was altering the object's motion was not a relic of its earlier journey. It was something acting upon it now within the domain of the sun. Nevertheless, astronomers continued pushing the reconstruction deeper into the past, exploring the possibility that the object had once belonged to a system no longer intact. Some simulations allowed the object to originate from a star that had either dimmed into obscurity or migrated far from its birthplace. Other models examined whether the object had spent eons in a gravitationally quiet corridor between spiral arms, a region where interstellar debris can drift without significant interference. Such environments are difficult to study because they leave almost no physical records, yet their existence provides a plausible backdrop for the object's calm approach. Spectroscopic clues from the object itself offered additional insight. Though faint and challenging to interpret, the reflected light suggested a surface that had endured high exposure to cosmic radiation, the kind typically found in regions far from the shielding plasma bubbles surrounding young star systems. This detail supported the idea that the object had spent an extraordinary amount of time drifting between stellar neighborhoods. Its surface chemistry appeared aged, weathered not by micrometeorite bombardment, but by exposure to the deep interstellar environment. This kind of surface evolution cannot be imitated by bodies confined to a planetary system. It requires vast spans of isolation. Piecing together these elements, researchers built a narrative of the object's distant past. It was likely a remnant of a long-vanished system, perhaps shed gently from a region, undergoing quiet evolution rather than violent destruction. It travelled across the galaxy with a composure rarely seen in interstellar visitors. That composure made its later deviations even more startling. The gentle origin suggested a body defined by passive motion governed entirely by gravity. Yet the current trajectory contradicted that assumption. Something new was influencing it, something that had not been part of its ancient journey. Tracing the origin of 3IATLAS did more than reveal where it came from. It laid the foundation for understanding what it should have been. A fragment shaped by peace should obey the rules of celestial mechanics without hesitation. Its defiance within the solar system hinted at an influence operating here in the Sun's domain, not in some forgotten corner of the galaxy. The backward reconstruction ended not with a precise birthplace, but with a portrait of an object from silence forged in calm, drifting through millions of years before arriving at a star whose gravitational authority it should have obeyed. The mystery lay not in its origin, but in the transformation that occurred once it crossed the solar system's invisible threshold. The moment researchers realized that 3I/Atlas refused to behave like a typical comet marked a turning point in the investigation. Comets have long been considered reliable archivists of cosmic history. Whether they originate from the Oort cloud or drift inward after spending ages in deep freeze, their behavior is shaped by simple and well-understood forces. As they warm, volatile ices sublimate into jets, producing gentle thrust that nudges their orbits. Their brightness fluctuates predictably. Their dust tails trace arcs sculpted by solar radiation and the solar wind. But 3I/Atlas began to defy those expectations almost immediately. Observers noted that its trajectory had already drifted from the curve predicted by gravity alone, and yet its physical characteristics did not align with any of the usual sources of non-gravitational force. The first clue came from its apparent stillness. Standard cometary bodies betray their nature early through feathery halos of vaporized material. These halos, called Comet, often bloom long before a comet approaches the Sun significantly. They reveal sublimation from frozen carbon dioxide and other volatile compounds. But in the case of 3I/Atlas, repeated imaging showed nothing of the sort. Even in deep exposures designed to capture faint emissions, the object remained visually stark. No haze, no tail, no uneven brightness. It appeared more like a compact asteroid than a frozen fragment. Yet the deviation of its orbit insisted that something was influencing it. When researchers plotted the residuals between predicted coordinates and observed positions, they found patterns that could not be dismissed as random scatter. The deviations accumulated consistently, forming a smooth sequence that demanded explanation. But each explanation fell apart under scrutiny. If the object were shedding gas symmetrically, the resulting force would be negligible and unable to generate the observed acceleration. If outgassing were asymmetric, it would have produced telltale fluctuations in brightness or rotational modulation. No such patterns appeared in photometric data. The object maintained a steady reflectivity as though nothing on its surface was changing. The refusal of the object to engage in comet-like behavior invited alternative interpretations. Some researchers proposed that the object might be composed of material unusually resistant to heating. That would account for the lack of sublimation. However, if the composition were dominated by refractory material, then the shape of the orbit should be governed almost entirely by the Sun's gravity. In other words, a comet that does not act like a comet should also move like an asteroid. But 3I/Atlas did neither. It moved with the freedom of something receiving an invisible push. This contradiction grew sharper when thermal measurements from mid-infrared surveys arrived. Data from these instruments indicated that the surface temperature of the object rose as expected when it drifted closer to the Sun. The thermal absorption and re-emission followed familiar physical laws, but if the heating were normal, then the absence of sublimation became even more perplexing. A body warmed in this way should bleed volatile gases, yet the spectral signatures showed nothing. Instead, the surface appeared to radiate heat smoothly without any geological or chemical disturbance. The object behaved like a stone gliding through sunlight, not an icy remnant of a distant star system. This left dynamicists with an unsettling problem. They were now observing a body that moved like a comet under invisible forces, but looked like a silent fragment with no internal activity. Objects rarely combine such traits. The combination forced scientists to confront a broader question. What if the defiance of cometary rules was not an anomaly in observation, but a genuine physical property of the object itself? As the orbit continued to evolve, a clearer picture emerged of the magnitude of the deviation. The acceleration was small but consistent, increasing gradually as the object moved deeper into the inner solar system. The shape of the curve hinted that the force did not originate from jets or internal pressure. Instead, the object seemed to shift in response to an influence that remained constant regardless of its orientation or rotation. This suggested an external factor. But the only significant external force at such distances aside from gravity would be radiation pressure. For radiation pressure to create a measurable effect, the object would need an extremely large surface area relative to its mass. Yet the light curve indicated a compact shape that did not exhibit the extreme elongation or reflective efficiency required. Attempts to reconcile these contradictions led to a series of simulations exploring exotic structures. One possibility considered whether the object might consist of porous or foamy material, giving it a low density. A low-density object could in theory respond more strongly to radiation pressure, but a fragment that light would rotate irregularly under the influence of solar photons. It would tumble unpredictably. Observations of 3I/Atlas showed no such behavior. Its brightness remained smooth, implying a stable rotation and cohesive structure. The object had now revealed its first signature trait. It refused classification. It was neither comet nor asteroid, neither icy nor active, neither dense nor fragile. It occupied an enigmatic position between categories contradicting the taxonomy that astronomers relied upon for centuries. This was the moment when researchers began referring to it with increasing caution, no longer using familiar labels, but instead describing it simply as a visitor with unknown physical behavior. The refusal to follow established rules also prompted reconsideration of the object's interior. Perhaps its composition differed radically from known bodies. Interstellar fragments can contain exotic ices, unusual isotopes, or mineral structures shaped by long exposure to cosmic rays. It was proposed that the surface might be coated in radiation-hardened material that suppressed sublimation. But this explanation still failed to address the acceleration. If nothing escaped the surface, no recoil should occur. The object had to be receiving its push from something other than its own chemistry. The deeper researchers looked, the clearer the contradiction grew. 3I/Atlas lacked the very features required to justify the way it moved. Its motion and its appearance were in conflict. The object presented itself as a riddle hidden inside a riddle, a contradiction travelling through the solar system with a calmness that belied the disorder it introduced into scientific models. By the end of this phase, the scientific community could no longer dismiss the object as a typical interstellar fragment. It had already displayed enough defiance to separate itself from every known category. The inability to fit 3I/Atlas into the established framework marked the threshold of a deeper mystery. Something was happening that did not align with the expectations shaped by centuries of celestial study. A visitor that should have behaved predictably was instead becoming the focal point of a paradox. The solar system had gained an occupant whose motion contradicted its nature. And the question now looming over the scientific world was no longer simply what the object was made of, but why it refused to act like anything humanity had ever seen. As the days passed and more observatories contributed their measurements, the scientific unease surrounding 3I/Atlas spread beyond the initial teams who first recognized the deviation. Orbital modelers whose work relies on the precision of gravitational mathematics began comparing calculated trajectories with nightly observations. What they found unsettled them profoundly. The differences were not dramatic enough to suggest catastrophic forces, but they were persistent, systematic, and disturbingly consistent. Whenever the predicted orbit was refined, the next set of observations arrived with yet another mismatch. This pattern repeated until it became impossible to attribute the discrepancies to measurement error. Something was affecting the object in a way that classical orbital theory could not account for. In the world of celestial mechanics, precision is sacred. The laws of motion governing planets, asteroids, and comets have been tested for centuries, verified by spacecraft navigation and countless observations. Even small bodies with irregular shapes or volatile rich surfaces usually conform to models once the correct parameters are introduced. Minor noise can always be resolved, calibration errors can be corrected, outgassing events can be modelled. But when the logical structure of orbital fitting begins to break down, it raises concerns far beyond a single anomaly. It threatens the coherence of the predictive framework itself. The computational teams working with the observational data attempted to impose increasingly detailed solutions. They experimented with models incorporating hypothetical jets, shifts in center, of mass rotational tumbling, and uneven thermal distribution. None produced a trajectory that matched the observed drift. When simulated jets were added to mimic sublimation, the resulting motion introduced irregularities that the real object did not display. The smoothness of 3I/Atlas's path contradicted the chaotic nature of cometary venting. Even when the direction of such jets was manipulated artificially to force a fit, the brightness data refused to cooperate. A jet powerful enough to create the observed acceleration should have left obvious signs across multiple wavelengths. Instead, the object remained visually calm. The failure of these models signaled something more than a missing variable. It suggested that the fundamental assumption itself might be flawed. The motion of 3I/Atlas appeared to follow a consistent influence that did not depend on rotation, orientation, or surface irregularity. It was as if an unseen hand had nudged the object, gently producing a steady acceleration unrelated to thermal processes. This made gravitational modelers increasingly uneasy. Comets do not receive perfectly aligned pushes that persist over long distances with no change in magnitude. Nature rarely produces such symmetrical behaviors unless some deeper hidden mechanism is involved. When the object crossed a region where solar gravitational pull should have begun dominating, the anomaly grew more pronounced. The orbit deviated in a direction that was neither aligned with the solar system's ecliptic plane, nor oriented toward any particular planetary perturbation. It was almost diagonal to the expected path, a motion that defied the clean geometry of celestial influence. Researchers accustomed to the elegance of gravitational curves found themselves staring at an arc that seemed to rewrite itself nightly, reshaping a mathematical portrait that refused stability. During this period, collaborative networks formed among dynamicists across the globe. Many had spent their careers calculating trajectories for spacecraft mapping, asteroid danger probabilities, or predicting cometary returns centuries in advance. These were individuals who trusted numbers more than intuition, yet their numbers were now delivering results that contradicted one another, depending on the assumptions used. Some orbital solutions diverged so drastically from reality that the errors exceeded what should be possible even with incomplete data. Others produced paths that aligned for a few days before spiraling into impossible projections. This mounting instability reminded some researchers of the challenges encountered when modelling Oumuamua's outbound acceleration. But those similarities extended only so far. Oumuamua's deviation had occurred after perihelion, when outgassing could have provided a subtle recoil even if unobserved. 3I/Atlas, however, exhibited its deviation both before and during its approach. The influence acted continuously, not episodically. It was not triggered by heating. It did not diminish with distance. Its constancy suggested that whatever drove the motion was independent of solar flux. The most troubling aspect of the discrepancy appeared when researchers examined how the deviation changed relative to distance from the Sun. If radiation pressure were responsible, the magnitude should have decreased at larger distances following the inverse square law. But in the case of 3I/Atlas, the shift remained steady. No clear relationship linked the object's distance to the strength of the anomaly. This observation generated widespread concern because it eliminated one of the few plausible mechanisms that could have explained a steady, directionally coherent acceleration. Several research teams attempted to fit the entire trajectory using modified equations of motion. These included experimental models that allowed for minuscule forces that typically fall below observational thresholds. Yet every attempt produced curvature mismatches. It became clear that the anomaly was not a subtle adjustment to known forces, but something foreign to the gravitational landscape astronomers understood. As the days accumulated, the phenomenon reached a critical psychological threshold within the scientific community. The incipient suspicion that the anomaly hinted at something deeper grew too strong to ignore. Some researchers proposed that the object could be interacting with a field not directly related to the Sun. Others wondered whether the observed motion could be a symptom of an internal structure, unlike anything previously encountered. But even these more speculative ideas struggled to reconcile the data. No known physical mechanism could produce a sustained directionally stable acceleration without releasing mass-altering brightness or inducing rotational wobble. The more the orbit was analysed, the more the discrepancies sharpened. They no longer appeared as random noise or isolated anomalies. They formed a coherent pattern that demanded a new interpretation of the forces at play. The situation grew so perplexing that some teams began re-examining the assumptions underlying solar system dynamics, searching for overlooked influences or rare edge case conditions. Yet every traditional pathway led back to the same impasse, a body that moved as if following a rule that does not exist in the catalogue of familiar forces. In time, the growing instability of orbital models forced scientists to confront a sobering conclusion. The behaviour of 3I/ATLAS was not the result of incomplete measurement or observational limitations. It represented a genuine deviation from the predictions of known physics. This realisation marked the end of the era when researchers hoped to fit the anomaly into existing frameworks. The object had crossed the boundary from curiosity to profound challenge, and the scientific shock that followed would not dissipate quickly, for it suggested that something fundamental about interstellar bodies, or perhaps about space itself, remained hidden from human understanding. As the investigation expanded, attention shifted toward a set of measurements that hinted at influences not accounted for in any conventional model of cometary motion. Researchers examined the object's residual acceleration with increasing scrutiny, searching for clues buried within the fine structure of its trajectory. When they filtered the data for subtle periodic variations, a faint pattern emerged, one that suggested the presence of a guiding influence unrelated to outgassing rotation or gravitational interactions with nearby bodies. It was as though the object responded to an external stimulus too gentle to produce visible effects, yet persistent enough to steer its path. This realization marked the beginning of an inquiry into forces rarely considered in the context of interstellar fragments. Magnetic effects were among the first possibilities examined. While comets typically carry traces of magnetized dust or minerals left over from their primordial formation, these traces are far too weak to generate measurable acceleration. However, when researchers analyzed the object's motion through regions of varying heliospheric magnetic intensity, they noticed a correlation that did not align perfectly, but suggested some form of interaction. The displacement was small, almost buried beneath noise, yet it appeared repeatedly when the object passed through zones where the solar magnetic field subtly shifted orientation. This prompted teams to investigate whether the object's interior might contain materials capable of responding to such fields more strongly than expected. Spectropolarimetric measurements provided the next clue. Observatories specializing in polarized light detected a slight but unusual rotation in the reflected signal. This rotation indicated that the surface of 3I/ATLAS contained grains capable of aligning partially with ambient fields, a behavior not common in standard cometary material. The possibility that the object carried a crust of magnetically active components introduced a new dimension to the analysis. If the surface or interior contained a significant concentration of ferromagnetic or paramagnetic compounds, then even faint heliospheric fields could exert an influence on its orientation. Yet orientation alone could not account for acceleration unless some internal mechanism amplified the effect. Researchers explored the idea that the object might harbour trapped magnetic domains, remnants of environments far beyond the solar system. Interstellar clouds can imprint magnetic signatures onto forming bodies, especially if they condense in regions threaded by strong galactic fields. If 3I/ATLAS originated in such an environment, it might carry a fossil magnetic imprint. This imprint, interacting with the slowly shifting heliospheric field, could alter the object's motion in subtle but measurable ways. However, the magnitude of the observed acceleration challenged this idea. Fossil magnetization should produce orientation changes, not directional thrust. Other investigations focused on the fine, particulate structure of the surface. Some researchers proposed that the object might be releasing tiny electrically charged dust grains, too small to produce detectable brightness variation. The electrostatic forces acting on these grains combined with the solar wind could create minute recoil effects. This idea gained temporary traction because the solar wind is capable of accelerating micron-sized particles at considerable speeds. But when high-resolution photometry was applied, the object displayed no irregular flickering or spectral shifts, corresponding to escaping charged dust. The reflectivity curve remained smooth, undermining the notion that the object was shedding mass covertly. Attention then turned to a more unusual interpretation. A few researchers suggested that the object might be interacting with an ambient field of unknown origin, something not accounted for in current heliophysical models. They examined the acceleration profile relative to changes in solar wind density, interplanetary magnetic field strength, and the distribution of charged particles along the object's path. A puzzling observation surfaced repeatedly. The acceleration seemed indifferent to fluctuations in solar wind velocity. It remained constant across regions where particle flow varied dramatically. This indifference complicated any theory relying on charged particle interaction. A force unaffected by environmental variation suggested a mechanism intrinsic to the object, or one tied to a background field that permeated space uniformly. This was when a few theoretical groups proposed an unexpected hypothesis. They wondered whether the object might be responding to gradients in the heliosphere's magnetic topology, in a manner similar to dust grains suspended in magnetorotational flows. Though such behavior is known only on microscopic scales, the idea that a macroscopic body could exhibit analogous tendencies intrigued researchers. If the internal composition of 3I/ATLAS allowed it to couple faintly with magnetic geometry, then gentle but consistent drifts could emerge. However, this would require a form of internal structure far more ordered than the porous, chaotic composition typical of comets. As models grew more detailed, a distinctive conclusion surfaced. The forces acting on the object were extraordinarily weak, yet the object's response was unusually pronounced. Something about its composition allowed it to react to influences that would be negligible for ordinary cometary material. Whether that influence came from faint magnetic gradients, a relic internal field, or an unrecognized physical process remained open to interpretation. But the key insight was clear: the object's deviation could not be attributed to chemical activity or outgassing. It originated instead from an interaction between the object and its environment at a scale more delicate than previously imagined. A broader question emerged. Why would an interstellar object possess such responsiveness? Nothing about the early observations had indicated fragility or unusual internal architecture. Yet the data now suggested that its material composition differed fundamentally from what the solar system had taught scientists to expect. It might contain mineral phases uncommon in local comets. It might preserve structural arrangements formed under pressures or temperatures alien to planetary systems born in calm nebular environments. Or perhaps its journey through interstellar space had altered it, bombarded it with cosmic radiation that restructured its crystalline matrix in ways that allowed external fields to influence it more readily. Another group of researchers focused on the consistency of the acceleration. They observed that although faint magnetic responses could align with the direction of the anomaly, the magnitude appeared too steady. They proposed that the object could harbour regions capable of storing electromagnetic energy, releasing it gradually as it rotated. This release, though extraordinarily subtle, could generate small but persistent thrust. Yet this interpretation required a level of internal coherence that bordered on exotic. It introduced the possibility that the object's material properties were not simply unusual, but perhaps entirely foreign to typical planetary formation scenarios. The search for a coherent explanation brought the scientific community to a crossroads. None of the proposed interpretations fully satisfied all observed conditions. The magnetic hints were compelling but incomplete. The structural theories offered possibilities but lacked proof. The dust grain hypothesis faltered under scrutiny. Amid this landscape of partial answers, one certainty emerged. The deviations displayed by 3I/ATLAS were not random. They were the signature of a systematic influence, an influence that hinted at forces acting quietly upon the object, leaving no visible trace yet shaping its journey with unwavering consistency. This realization pushed the investigation into deeper territory. if an unseen force guided the object, and if that influence was tied to properties intrinsic to the fragment, then understanding the object required exploring physical processes at levels seldom considered for interstellar remnants. The mystery had shifted. It was no longer simply about why the object moved strangely. It was now about what the object truly was, and what unknown structures or fields it carried with it as it drifted through the solar system like a messenger from environments humanity had not yet studied or imagined. When astronomers turned their attention to the light curves recorded during the first weeks of observation, they expected the usual complexities associated with a rotating interstellar fragment. Normally, small bodies tumbling through space reveal themselves through rhythmic fluctuations in brightness. These changes emerge from their uneven shapes, patchy surface albedo, and shifting reflective angles as they spin. The pattern may be irregular, but it is always traceable. Yet the early light curve of 3I/Atlas refused to behave like the familiar signatures catalogued from countless comets and asteroids. Instead of the gentle periodic rise and fall expected from rotation, the data revealed variations that seemed to carry contradictions within them, as though the object rotated in ways that defied intuitive interpretation. The first anomaly appeared in the photometric symmetry. Researchers noticed that the brightness remained remarkably uniform over extended periods, with only faint modulations too smooth to resemble the jagged changes expected from an elongated or unevenly reflective surface. This suggested a body with an unusually balanced shape, perhaps nearly spherical, or possessing an unexpectedly homogeneous coating. Yet infrared data hinted at subtle rotational heating patterns, implying that the object did indeed rotate and did so with a slow, steady rhythm. The contradiction deepened. How could a rotating body produce such a calm optical signature, unless its surface absorbed and emitted light in an typically uniform manner? A closer examination of the curve revealed an even more puzzling detail. At specific viewing geometries, the brightness shifted slightly in ways that did not correspond to the thermal pattern. The wavelengths most responsive to reflected sunlight showed minuscule dips and rises that could not be attributed to shadows vents or surface roughness. Instead, these faint oscillations resembled interference patterns. Some researchers proposed that the object might possess surface grains capable of scattering light in coherent ways, creating effects similar to polarized glints. These glints, when combined with the object's slow rotation, could produce a light curve that appeared deceptively stable. Other teams focused on the possibility of layered structure. If the object possessed a crust with alternating zones of dense mineral composition and porous material, then the reflected light might remain constant while the thermal output varied. This kind of stratification has been considered for certain trans-Neptunian bodies, but has rarely been discussed for interstellar fragments. The idea gained traction when spectroscopic studies detected faint signatures consistent with irradiated organics and metallic inclusions. Such combinations could create optical surfaces capable of diffusing light with unusual consistency. Additional insights emerged from high-precision photometry obtained during a sequence of nights when atmospheric conditions were exceptionally clear. These data revealed a subtle heartbeat-like pattern in the brightness, a periodic offset too slow to be attributed to tumbling yet too regular to be noise. Some researchers interpreted this as evidence of an internal rotation distinct from the surface rotation. In this scenario, the object's core might rotate independently, perhaps due to internal mass distribution shaped by the pressures and temperatures of interstellar formation. If the interior shifted independently even slightly, the surface could respond by bending or flexing in microscopic ways, producing delicate shifts in reflectivity. This idea aligned with models proposing that some interstellar objects might not be monolithic but rather exotic composites, created through slow accretion in environments far from the gravitational pressures of star-forming regions. Such bodies could develop layered internal structures with mechanical behavior unfamiliar to the solar system. If 3I/Atlas possessed such internal dynamics, then its light curve would naturally resist straightforward explanation. Yet another detail emerged when deep field imaging captured the fragment in wavelengths sensitive to extremely fine dust. Although no classical coma appeared, a faint halo of microparticles surrounded the object in a configuration unlike typical dust clouds. These particles remained tightly bound to the object, drifting in patterns that hinted at electrostatic adhesion rather than gravitational cohesion. If these grains were distributed unevenly across its surface, the reflected light could appear smoother than expected despite underlying irregularities. The presence of such an electrostatic sheath would also suggest that the object held a charge distribution capable of interacting subtly with solar wind particles, potentially contributing to the small forces influencing its motion. The deeper researchers probed, the more the light curve revealed a form of elegance rarely seen in primitive bodies. Instead of chaotic fluctuations, it displayed a serenity that seemed almost intentional. Every correction applied to the data removed one inconsistency only to reveal another. Each refined model explained part of the curve while leaving a new element unexplained. The object behaved like an artifact shaped not by violent ejection or collisional fragmentation, but by a slow, deliberate process that produced a surface capable of interacting with light in remarkably complex ways. Another suggestion came from groups studying crystalline structures formed under rapid cooling and interstellar shocks. Such crystals can possess optical properties unlike anything produced within the solar system. If 3I/Atlas contained a surface coated in such minerals, its light curve might naturally produce the smooth signatures observed. These coatings could scatter incoming sunlight, evenly mask underlying irregularities, and give the appearance of stillness even as the object rotated steadily. But the most intriguing possibility arose from an analysis comparing brightness variations with the object's anomalous acceleration. Some researchers noticed that the faint dips in brightness correlated subtly with periods when the orbital deviation sharpened. The correlation was not perfect, but it was significant enough to raise questions. Could the same structural property influencing the object's reflectivity also be tied to its reactive force? If so, then the light curve was not merely a record of shape and rotation, but a window into the physical mechanism driving the mysterious motion. This interpretation, while speculative, shifted the narrative. If the object's brightness pattern subtly mirrored its acceleration, then something deeper connected its appearance to the forces acting upon it. Perhaps its internal composition responded to fields that varied with position. Perhaps the grains on its surface rearranged themselves microscopically, altering both light reflection and internal stress. Or perhaps the object existed in a state where external influences shaped its behavior at levels too delicate to detect through conventional means. By the time analysts compiled all available photometric data, the conclusion was unavoidable. The light curves of 3I/Atlas contained clues that were impossible to reconcile with the classical behavior of any known comet or asteroid. They hinted at structure composition and surface processes that operated with a level of subtlety foreign to solar system dynamics. In these faint patterns, astronomers saw the early expression of the mystery that would later deepen into something far stranger, a visitor whose interaction with light and motion suggested a complexity that demanded far more than simple gravitational modeling. When 3I/Atlas drifted past Mars, the scientific community expected a period of clarity. The planet's orbit provided a convenient geometric baseline. Its proximity to the object relative to earlier observation points offered an opportunity to refine measurements with unprecedented precision. As the interstellar fragments swept through the region where Mars and its thin atmosphere circled the Sun, researchers anticipated that the encounter would settle the uncertainties surrounding its motion. Instead, the observations gathered during this passage became the most troubling dataset yet, revealing a pattern of accelerations that defied every model prepared in advance. The first indications emerged within hours of the object entering the observational corridor monitored by Mars orbiters. Instruments aboard these spacecraft routinely calibrate their sensors by tracking stars and nearby objects, ensuring stable measurements for ongoing missions. When they turned their attention toward 3I/Atlas, the expected coordinates were offset more than predicted. The deviation was small, on the order of fractions of an arcsecond, yet far beyond what those spacecraft usually consider acceptable error. Mission teams repeated the measurements, checked for instrumental drift, examined attitude control logs, and reviewed internal calibration cycles. Nothing pointed to malfunction. Shortly after, ground-based observatories confirmed the discrepancy. Telescopes in Chile and Spain tracked the object across a sequence of exposures, each independent and collected under excellent atmospheric conditions. Their measurements matched the orbital data from Mars orbiters, almost exactly ruling out spacecraft error. The anomaly was real. At the moment when gravitational influence should have been easiest to model, the object's trajectory showed another shift, and this time the deviation grew larger as it passed behind Mars from Earth's perspective, where the planetary geometry tightened the baseline for parallax measurements. The most perplexing result came from combined datasets. When researchers plotted every point gathered during the encounter, a clear pattern formed. 3IATLAS experienced a rise in acceleration as it passed Mars. The effect was not dramatic, but it was unmistakable. During the closest approach, the object deviated from the predicted curve by an amount too large to attribute to observational noise and too small to indicate any kind of explosive event. It behaved as though an invisible hand applied a soft, steady pressure nudging it into a slightly different path as it moved through the gravitational neighborhood of the red planet. This behavior fascinated dynamicists because Mars, with its modest mass, should not have altered the trajectory significantly. Planetary perturbations are well understood, and no hidden mass lurks near Mars capable of producing such influence. The anomaly was also too smooth to be attributed to local dust suspensions or solar wind fluctuations. If anything, the solar wind was relatively stable during the object's passage, with no major disturbances recorded by heliophysics monitors. Another clue emerged from infrared imaging captured by the Mars Reconnaissance Orbiter. These scans detected a subtle thermal offset on the object's surface. The temperature distribution was slightly asymmetric, but not in the way expected from solar heating. Instead of warming on the hemisphere facing the sun, the object displayed a faint increase along a region angled slightly away from direct sunlight. This anomaly, though extremely subtle, suggested an internal process or a surface composition that responded to environmental conditions in ways not fully understood. If the thermal variation influenced the object's structural integrity, it could produce micro-level shifts that contributed to the unexpected acceleration. Meanwhile, spectroscopic data recorded during the encounter deepened the confusion. Mars orbiters detected no gas release, no dust shedding, and no evidence of chemical activity. If a comet were accelerating due to sublimation, traces of water vapor or volatile compounds should appear even in faint quantities. Yet the spectra were silent. The absence of any tail or coma became even more significant. The closer the object approached the Sun, the more one would expect sublimation. But 3I/Atlas remained inert, almost eerily quiet. Another set of observations came from the timing of occultations. As the object passed in front of distant stars, from the perspective of instruments near Mars, tiny dips in starlight allowed researchers to map its silhouette at high resolution. These occultation curves revealed a shape that was strangely regular. The outline lacked the irregular protrusions typical of natural fragments. Instead, the edges appeared smooth, almost engineered by long geological processes that did not resemble the chaotic assembly of most comets. Its form seemed neither elongated nor jagged, but gently contoured as though interior forces shaped it over immense periods of time. One of the most striking discoveries came from an analysis comparing acceleration with the solar wind particle density near Mars. During the closest observations, the solar wind carried a relatively uniform particle flow, yet the object's acceleration increased slightly during a period when solar wind fluctuations dipped, contradicting any model that relied on charged particle interactions. If anything, the acceleration should have decreased. Instead, the anomaly sharpened. The acceleration appeared to operate independently of environmental conditions, driven by something intrinsic rather than reactive. These findings led several researchers to revisit earlier assumptions. They proposed that the object might possess internal structures capable of responding to gravitational gradients in highly unconventional ways. Perhaps its interior contained materials that expanded or contracted at microscales, producing thrust too gentle to cause visible jets, but strong enough to alter trajectory. Others considered whether the object might carry trapped energy from ancient cosmic events, slowly releasing it as it experienced new gravitational environments. These ideas remained speculative, but they demonstrated the growing recognition that standard explanations no longer sufficed. As more data accumulated, the passage near Mars became a cornerstone of the mystery. It not only confirmed the object's anomalous acceleration, but also indicated that the effect intensified in ways not tied to the solar system's known fields. The encounter revealed a visitor whose behavior seemed to awaken when interacting with planetary environments. The closer it moved to internal gravitational structures, the more distinct the anomaly became. By the time 3I/Atlas moved beyond Mars, leaving behind a trail of perplexing measurements, the scientific world realized that the fragment was not merely unusual. It was operating according to a set of rules unaccounted for in established physics. The red planet had served as an observer to a phenomenon subtle enough to evade direct detection, yet powerful enough to reshape orbital predictions. A quiet shift near Mars had now become a central piece of evidence. Something was influencing the object with a consistency that pointed beyond the conventional understanding of cometary dynamics. The solar system, it seemed, had become a testing ground for forces that resisted explanation. And the encounter with Mars marked the moment scientists fully accepted that the mystery surrounding 3I/ATLAS was only deepening. As multi-wavelength observations converged from observatories across Earth and orbiting instruments scattered throughout the inner solar system, a picture began to take shape that resisted simple interpretation. Each wavelength told a different story. Where visible light suggested smooth stability, infrared scans revealed minute thermal irregularities, and ultraviolet imaging exposed scattering behaviors that few researchers had anticipated. When assembled into a single framework, these datasets painted an object whose properties shifted subtly depending on how it was observed, as if each region of the electromagnetic spectrum illuminated a different layer of its identity. This was not unusual in itself. Many celestial bodies reveal distinct faces under different wavelengths. What rattled astronomers was that these faces did not fit together. The visible spectrum portrayed 3I/ATLAS as a calm, muted body with no signs of jets, eruptions, or sublimation. Its reflective surface behaved like a mixture of darkened minerals and radiation-aged compounds, the kind expected after millions of years drifting between stars. Yet the near-infrared data contradicted the impression of uniform stillness. Slight temperature variations were detected across the object's surface, arranged in a pattern that did not align with the sun's heating profile. Instead of the hemisphere facing the sun being consistently warmer, several patches of elevated temperature appeared along an arc tilted away from direct sunlight. This arrangement implied that internal structure or buried material layers responded to sunlight in a non-uniform way. At the same time, ultraviolet imaging unveiled faint streaks of scattered photons, a signature that hinted at exceptionally fine particles surrounding the object. These particles were too sparse to be considered a true coma, yet they influenced the ultraviolet reflectance strongly enough to raise questions. Their distribution appeared uneven, almost sculpted by electrostatic interactions rather than continuous shedding. If these grains hovered near the surface due to charged interactions, they could theoretically affect how the object responded to solar radiation at multiple wavelengths. But the pattern was too subtle to offer a definitive explanation. Matters grew more complicated when mid-infrared readings from space-based telescopes highlighted sharp contrast between surface regions. A handful of localized warm points appeared, but without the corresponding spikes that should occur if sublimation were responsible. Normally, as a comet releases volatile ices, thermal signatures display irregular bursts and expansions, yet here the warm points remained stable. They did not expand outward or flicker. Their quiet persistence suggested a form of internal conduction, perhaps through buried materials with higher thermal inertia. If the interior contained pockets of dense mineral compounds or metallic nodules, these could absorb and store heat differently from the surrounding substrate. Radio frequency scans contributed another layer. These observations hinted at irregular dielectric properties that complicated current models. The surface seemed capable of absorbing certain radio frequencies, while reflecting others at angles inconsistent with a rough or porous composition. Such behavior suggested regions of crystalline alignment or microlayering patterns that sometimes arise in bodies that have undergone long-term radiation processing in environments with strong cosmic ray exposure. This kind of internal coherence could influence how external forces acted upon the body, potentially explaining the object's unusual reaction to minimal environmental cues. When scientists overlaid all these findings, they confronted a dataset filled with incompatibilities. The ultraviolet halo implied delicate dust suspended through electrostatic effects. The infrared asymmetry pointed toward internal thermal pathways shaped by exotic material composition. The radio reflectance suggested crystalline structure with ordered domains. Yet the visible spectrum showed none of the behaviors typically associated with these traits. Ordinarily, an object exhibiting such multi-layer complexity would reveal at least some form of active behavior. But 3I/ATLAS remained visually inert, as if concealing its workings beneath a meticulously stable exterior. Some analysts propose that these inconsistencies were not contradictions but clues, hinting at a structure fundamentally different from solar system comets. They explored the idea that the object's surface might consist of compacted layers of minerals hardened by centuries of cosmic irradiation, burying volatile materials beneath a crust impenetrable to sunlight. Such a crust could modify how heat propagated, slow the rate of sublimation to negligible levels, and distort reflectance in ways that only became apparent under certain wavelengths. Yet this interpretation struggled to explain the ultraviolet halo, which implied microparticles and charge dynamics that would require at least some level of surface disturbance. Another group examined the possibility that the interior housed materials formed in extreme environments, perhaps near a dying star or within a region, influenced by high-energy shock waves. Such materials might carry structural asymmetries capable of interacting faintly with magnetic or electric fields, producing small steady forces as the object rotated. These forces would not resemble sublimation jets, but could nevertheless influence trajectory. If so, the multi-wavelength anomalies could be signatures of internal transitions or stress patterns. But this idea required an interior complexity rarely attributed to interstellar fragments. The deeper researchers pushed their analysis, the more the object behaved like a composite of incompatible elements. The fine dust suggested fragility. The thermal anomalies suggested density. The radio response suggested organized crystalline domains. The visible calm suggested an unbroken surface. Reconciling these factors required a model that allowed the object to be simultaneously hardened and delicate, structured, yet stable, inert, yet reactive. As tension grew within the scientific debate, one detail gained prominence. The anomalies intensified whenever the object moved through regions where the solar system's magnetic landscape subtly shifted. It was not an obvious correlation, but it remained consistent across multiple datasets. Whenever the heliospheric magnetic field changed direction, or strength due to solar rotation or local disturbances, certain wavelength readings from the object fluctuated slightly. These fluctuations were faint but statistically significant. This suggested that the fragment possessed material properties sensitive to magnetic topology, aligning with the idea of exotic minerals or cosmic ray processed crystalline formations. This correlation provided a tentative bridge linking the multi-wavelength anomalies to the earlier orbital deviations. If the object reacted to magnetic fields in ways ordinary comets do not, then its internal structure might possess magnetically responsive domains capable of exerting microscale influences on its motion. Such interactions would be too small to detect directly, but could accumulate into the steady acceleration observed. By the end of the multi-wavelength campaign, scientists had assembled an intricate tapestry of clues. No single explanation united them, yet each pointed toward a visitor shaped by environments the solar system had never been exposed to. The object carried hints of microstructured material radiation, processed surfaces, electrostatically suspended particles, and thermal behaviors inconsistent with simple ice-rock mixtures. The spectrum of evidence revealed not a chaos of data, but a layered complexity that suggested the fragment was a relic of processes operating beyond the typical boundaries of planetary formation. In these contradictory wavelengths, astronomers sensed the quiet outline of a deeper mystery. 3I/Atlas was not simply an interstellar wanderer obeying familiar rules. It was a carrier of unfamiliar physics presenting itself in fragments of light that refused to settle into any comfortable category. And the more wavelengths revealed, the clearer it became that this object would demand interpretations far beyond the conventional framework of cometary science. As global observatories pooled their measurements into unified datasets, researchers anticipated that the synthesis would resolve some inconsistencies and clarify the nature of 3I/Atlas. Instead, the combined analysis produced results that strained comprehension. When observations across visible light-infrared emissions, ultraviolet scattering and radio reflectance were merged into a single physical model, the outcome revealed a portrait of a body whose characteristics simply did not align with known categories of celestial objects. It was not that the data conflicted in small, manageable ways. It was that the data pointed in directions so divergent that no single framework could accommodate them without breaking fundamental assumptions. The first layer of confusion emerged from shape reconstructions. Using occultation curves, rotational light curves, and thermal gradients, analysts expected to derive a three-dimensional structure consistent across modalities. Yet each method provided a different interpretation. The silhouette suggested a body with gently rounded contours. However, the thermal distribution implied an internal architecture with sharp transitions between high and low conductivity zones. Meanwhile, polarized light hinted at smooth, fine-grained surfaces, while radio reflection patterns responded as though encountering faceted or crystalline microstructures. These perspectives did not describe different versions of the same object. They described objects that should not be able to exist together. When researchers attempted to build a composite model, they encountered contradictions impossible to reconcile. The smoothness implied by visible reflectance was incompatible with the angular scattering behavior detected in certain ultraviolet measurements. The coherent structures inferred from radio frequency response could not coexist with the porous textures needed to explain the faint dust halo. Attempts to map these features into layers also failed. If the surface were uniformly compact, the dust should not persist. If the interior contained dense crystalline domains, the thermal behavior should exhibit sharper responses. The object seemed to possess mutually exclusive characteristics, each undeniable in its respective dataset. Mathematical fitting routines, usually capable of merging disparate observations into a stable solution, produced outputs bordering on absurdity. One model required materials with both extreme brittleness and high tensile strength. Another demanded density variations that shifted by orders of magnitude within meters. A third required thermal inertia so high that the surface should remain cold despite solar exposure contradicting infrared measurements. These outputs resembled conceptual extremes rather than physically coherent bodies. Compounding the confusion was the behavior of the object's momentum. When researchers applied the full combined dataset to dynamical simulations,